Good afternoon, pre-calc folk. We are here with another Rockpile Tutors homework helper video. Today we'll be doing the homework for pre-calc for the Plymouth Canton and Salem pre-calc students. We will be going over section 4.8, applications and models, and doing the checked homework problems. So first we're just going to go generally over the section, and I'll give you my take on them. And let's see if I can do this right. All right. First thing we're going to do is we're going to talk about applications involving right triangles. You'll have a whole lot of these, and once you know how to do a right triangle, you're going to look for opportunities to make right triangles. So the main thing we do here is we need to remember that all the trig stuff comes back to SOHCAHTOA. Right? Sine is the opposite over the hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. Now, what does that all mean when you're looking at a triangle? So, if this is the angle, we're going to call that theta. This is the hypotenuse of that. That one won't change depending on the angle. From here, the side with the same letter, or the opposite side, is the opposite. And then, if they've got them labeled, the side with the different letter than the angle is the adjacent. Okay, hopefully you'll be able to remember that. So the way we solve these is we figure out what we have, and then we set up one of these three trig functions that includes that variable, both that includes a variable and the two pieces of information that we know. So for instance, with this one, if they want us to find A, we know that our angle is 34.2. I've got the adjacent and I want the opposite. So I want things that involve O and A. What is that? That's tangent. So what I'm going to do here is the tan of 34.2 equals opposite, what I'm looking for, A, over adjacent, 19.4. Now I'm going to go A equals 19.4 times the tan of 34.2. Desmos is your friend. What are we doing here? As I said, Desmos is your friend. A equals 19.4 times tan of 34.2. Okay, and we check it out, and it makes sense. No, it doesn't. Look, how do I have a negative answer? You know what I could be doing? I could be using radians. So let's check that out. Hey, look at that. I'm using radians. If I switch it to degrees, all of a sudden I get a more reasonable answer. So this is why you always want to make sure that your answer is reasonable, right? For instance, a negative side length means you've done something wrong, either setting up the equation or, in this case, radians versus degrees. Because 34 radians would be about a little more than 10 pi, if you can think about it, because 34, well, a little more than 10 pi, which will be a little more than 5 times all the way around, and that's why we ended up with a funky number. So check it, and now that we're in degrees, this should be about right, 13.18. All right, the next concept we are going to go over is let's put that up there so we can use it later. Okay, the next thing we're going to do is finding the side of a right triangle. And so the way I'm going to do that is I'm going to set up a right triangle. Here we've got a couple of the examples that they did. And let's set that up over here and work on it. Okay, So the setup we have here is that I've got a building, a distance away from it, an angle, and the length of that ladder. All right, so what I'm going to do is I'm going to make myself a triangle. I've got A, B, and C, right? Let's pretend that's a right angle, right? Here we have A, B, and C. And I have this angle theta. Theta is 72 degrees. So again, and what's the question? The question is, okay, if I want to find B, B is the adjacent side to theta. So the cosine of 72 is adjacent over hypotenuse. The sine of 72 is going to be the height, or A, the opposite side over the hypotenuse. And that's pretty much how you solve all of these problems. Find the word problem, figure out what your triangle is that you're trying to do, and then solve it like it was a regular triangle without all of that context. I think it's relatively easy to do once you start seeing the triangles, but that's the hard part. So we're going to learn how to do a triangle in space, and then we're going to learn how to see the triangle in the word problems that they're going to get you. Nah, we won't do another one until we get to the problems. Okay, and then the next thing we're going to look at is angles of elevation and depression. So the best way for me to understand this is that you're generally going to have two objects. It's either going to be, a boat and a submarine, a plane and a house, but one of them is going to be a different height from the other one, okay? And what I want you to do is figure out from the point of view of the thing, right? Is it looking up or down? So if this is my plane and this is a house, if they want the angle of depression, I put myself on the plane heading this way, and then the angle is the angle that I look down. So that's the angle of depression. If I'm sitting in the house, right, then I'm looking up, and this is the angle of elevation. Once you find that again, all we're doing is we're setting up the triangle to turn it into a simple triangle. And so if they're asking for this other angle, let me change the colors here. If they're asking for this angle, this is going to be 90 minus the angle of depression, because this is a right angle and they're complements. And similarly, they ask this over here, this is going to be 90 degrees minus the angle of elevation. So once you have that, you're setting up a transversal. You can also see that depression and elevation are the same, but depending on what they give you, you need to understand what angle you're dealing with. Now, additionally, what they'll often throw into you is a height offset at either the bottom or the top. So if we look at this, the height offset is this 1.3 underwater in the pool. And the way we deal with that is we just picture a rectangle under or over or next to or whatever they do to my triangle. I'm going to solve for the triangle, where this is, I don't know, AB or A, C, and B. And then I'm either going to add or subtract this height depending on what the question is. Often this will be the height of a person doing the seeing, and they'll put them 5 feet or 6 feet off the ground because that's where their eyes are. But just be aware when the height of the viewing is not the same as the height that they're asking in the problem. You may have to add or subtract a rectangle somewhere in there. Okay. All right, next. Side of a right triangle, angle of depression, angle of elevation. Okay, bearing. So now we're going to talk about how ships, well, how ships navigate and how to read different ways of saying what direction you're going. So in this case, we have to think about the north, south, east, west. I'm going to blow that up. I'm going to use theirs. All right, so for north, south, east, west, everything goes off of the north-south and it takes the acute angle between them. So for instance, the acute angle here is from the south toward the east. So that will be written as south 35 degrees east. All right, this one, it's going off of the north. So this is going to be from north to west, 80 degrees, or north 80 west. Again, 45, north 45 east. That's really all it is. It's essentially a language that we need to understand and be able to do math with. All right, the next thing you will see here, where are you? All right, the other thing that you'll see hours, minutes, and seconds, or degrees, minutes, and seconds instead of decimal degrees. And we're going to figure out how to change those. So if I have 47 degrees, 40 minutes, and 16 seconds, how do I do this? So normally with decimal, we're just dividing things by tens, hundreds, and thousands. In degrees, minutes, and seconds, we're using the clock metaphor. And so there are 60 minutes in every degree and 60 seconds in every minute. So if I have 47 degrees, 40 minutes, and 16 seconds, what I'm going to do is I'm going to do 47 plus 40 sixtieths of a degree plus 16 sixtieths of a minute. Sorry, 60ths of a minute, which was already a 60th of a degree, which is going to end up being over 3,600. So if you have degrees, minutes, seconds, what you're going to do is you're going to do 47 plus, you're going to do it this way. You're going to do 47 plus 40 over 60 plus 16 over 3,600. And I'm going to get that. Okay. Now, if we want to go the other way, if you've given a decimal degree, which is how you're mostly going to get it coming out of the calculator, and we want to go the other way, what do? We're going to do the opposite. But this one, a couple steps in between. So let's say I have let's go 37.418 degrees. Okay, and I want that to be degree, minutes, seconds. So first I'm going to figure out my minutes. So it's going to be 0.418. Here we go. Let's do this. So minutes is degrees times 60, right? Because degree is minutes per 60. So what I'm going to do is take 0.418 and multiply by 60, and I'm going to get 37. So that's going to be 37 plus 25 minutes, 37 degrees, 27 minutes. Now I'm going to take the decimal from my minutes, what's left over from the minutes, and I'm going to go 8 times 60 again, because the portion of my minute needs to become seconds. And I'm going to do 0.8 times 60. 0.08 times 60, and I'm going to get 4.8 minutes. Sorry, 4.8 seconds. Try that. So that's how to go both ways with degrees, minutes, seconds. And there's all sorts of problems like that, but we're still getting back to a triangle and then solving the triangle. And then the last bit is harmonic motion, which doesn't have anything to do with triangles, but is in applications where you'll see this a lot, almost in physics type things. And so the displacement, they're generally, a lot of times you'll see this as a weight on a string, and it's going to go up and down with no friction or anything like that. It's going to go up and down the same amplitude every time. And what it turns out is that that translates well into a sine or cosine, depending on whether it starts at 0 or starts at the end of the amplitude. So the way that we're going to see these is that typically they're going to describe it. So we'll do this problem here. So the problem is that the string, or the ball on the spring, is going to go from -10 to +10, and it'll oscillate back and forth. So what we want to do is we want to find the amplitude. So the amplitude is from 0, what's the biggest it gets. So the amplitude is 10 centimeters. The period is the amount of time it takes to go from one spot and finish the cycle. So if we start up here, it'll go all the way down, then all the way back up, and that's one period, and that's often measured in seconds. Okay? The other way you might see it is frequency, which is the number of cycles that happen in a second. Typically, electronics will move at 60 hertz or 60 cycles per second. In this case, if the period is 4 seconds, then the frequency is 1 cycle per 4 seconds, or 1/4. Okay, and that is how we set up the units for harmonic motion. All right, with that, let's go into the problems. Start with number 5, which is just using a basic triangle and solving the triangle. So we need to find all the sides and all the angles. Number 5, let's go over and take a look at it. Okay, we're going to set up our triangle. Our angle theta A is 30. Set it up. Sides are A, B, and C. C is the hypotenuse, A is the opposite side, and B is the adjacent side. We know that B is 10. So what we want to do is we want to find A and we want to find C. Those will be the sides. But first, let's get the easy stuff out of the way. Let's find the angles. So we know that that's a right angle, which means that B is 180 minus 90 plus 30, or 90 minus 30, which is 60 degrees. And now let's go ahead and find A. We know that we're going to be using trigonometry, so probably we're going to have SOHCAHTOA somewhere in the play. And in this case, I've got the adjacent. I want the opposite, so I'm going to use tangent. So the tangent of 30 is going to be equal to A over 10. We're going to rearrange algebraically and get A equals 10, 10, 30. And hop over to Desmos. You can see I've already done that. And so we get 5.77. Put that up here. Okay, we can also do that using the 60-degree angle, just so that you know you have flexibility. So if we want to do the tangent of 60, that would be its opposite, which is 10, over its adjacent, which is A. That'll flip things over. So A equals 10 over tangent of 60, which is also 5.77. We'll go ahead and put that up on the triangle and attack C. For C, I've got adjacent and I want the hypotenuse. So that's going to drive me to cosine. So the cosine of 30 is equal to 10 over C. Similarly, I'm going to adjust it. 10 over cosine 30. And I do that right here. And I see that I've got 11.54. Pop that up there. And now we're solved. So how do we check this? Let's check by using the Pythagorean theorem. All right. If I have my triangle there with my sides. How do I check if it's correct? Well, 5.77 squared plus 10 squared should equal 11.54 squared. If I come over here, 10 squared plus 5.77 squared is 133.2929, and the square root of that is 11.54. Probably rounded, probably should have been 11.55. Yep, 11.55, but you guys can get that. And that is how we do problem 5. So now, to finish it up, your answer should be, have labeled ABC, label your three sides, and label your three angles. Please put the right angle in there. I didn't do that. I will do that right now. Boom, there we go. All right, next problem is number 19, talking about a ladder up on the side of a house. So, first thing we need is a house. Man, I wish I could have a house like this. But we have a ladder leaning up on the side of the house, which is 20 feet long. And then if I draw the base, the angle of elevation is 80 degrees. Not drawn to scale, but we'll see what the numbers look like. So what I'm looking for is the height where the ladder touches the height to the ground. So that's going to be H. Now we've got our triangle set up, and it's time to do some trigonometry. So since we know that I've got the opposite and the hypotenuse, better label those on the triangle, that my sine of 80 is going to be the height over the hypotenuse. Rearrange that, check the math over here, and we have that the height where the ladder touches the house is 19.69. In reality, that's going to be a much more vertical triangle than I drew at first, looking more like this, because you can see the top of the ladder is barely below that 20 feet, because that first 10 degree that you tilt out isn't going to drop the height very much. All right, that is number 19. Let's look at the next one. All right, next problem we have is number 25. We have a church with a steeple. So we need to find ourselves a church with a steeple. There we go. And we have 50 feet in front of the church. We'll go out to the right here. The angles of elevation to the top of the church, or the base of the steeple, and the top of the steeple are 35 and 47 degrees 40 minutes respectively. First thing we want to do, label our 50 feet and label that height. So first thing we want to do is draw the two triangles. So we're just going to separate them. And that should be part A. Part B, we're supposed to find the height of the steeple. So I'm going to define my two heights, the height of the church and the height of the steeple, and I'm going to find them both. So the height of the church, what do I have? From the 35 degree angle's point of view, height is opposite, 50 is adjacent. So my tan of 35 is going to be the height over 50. Blow that out over Desmos, and I've got 35 feet. Okay, now I'm going to find the height of the steeple. Similarly, first I need to do degrees and minutes into degrees. So from what we did at the beginning, we know that's 47 plus 40 over 60 degrees. So the tangent of 47 degrees and 2/3 is that over 50. So the height of the steeple is, height to the top of the steeple from the ground, sorry, is 50 tan 47.67, which comes out to 54.89. Now I'm not sure if the question is asking for the height at the top of the steeple or the height of the steeple itself, but to find that, I would take the top of the steeple and subtract the bottom of the steeple, and that would give us 19.88 feet. And that's how we do it. All right, next we're going to do number 31. And this requires a little bit of mental understanding in figuring out what they're giving us and what the triangle we want to work on is. So what we want to do on this one is first I want to draw it from the point of the view of the satellite, because we're talking about angles of depression and elevation. So the satellite, although it's on a curved path, right now it's heading tangent to its path. So let's say it's going that way. They're telling us that it is 12,500 miles above that surface of the Earth. And then they're going to take 4,000 miles over to the horizon from the GPS, from the satellite's point of view. So that's where it's tangent to Earth. Now they're showing that as the right angle here, and that's the key to this triangle. Because after we do that, now what I want you to do is I want you to rotate that triangle so that the right angle is going straight down. I want you to do that in your mind. And from there, we can find out that the angle of depression is what we're looking for, but the angle inside the triangle is 90 minus that angle of depression. So now I'm going to rotate that triangle clockwise from the way I've drawn it. Draw that right angle in there. I've got my angle, and I've got my 12,500 feet and my 4,000 feet. Okay? So I've got a triangle set up. I've now got my hypotenuse and my opposite, so I'm going to be using sine, and the sine of 90 minus the angle I'm looking for is 4,000 over 12,500. So to find that angle, I'm going to do the inverse sine. So I'm going to do 90 minus theta. I'm going to get rid of that abbreviation and just put a Greek letter in there. So my angle that I'm looking for, the final answer, that angle of depression, is theta. So 90 minus theta, right, is the inverse sine of 4,000 over 12,500. Right? Think through that one. But that's how we're going to find it. Now I'm going to do a little bit of algebra. Get negative theta is that sine minus 90, and then turn it positive. So theta is 90 minus that sine. Desmos is your friend, and your answer is 71.34 degrees. If I want to turn that into degrees, minutes, seconds, I'm going to go take that 0.34 and figure out how many minutes it is, 20, and then I'm going to take that 0.4 of a minute and figure out how many seconds it is. And there we have our answer. Next, we have number 37. Looks like we've got 3 more to go. Ship leaves port at noon and has a bearing of south 29 degrees west. Well, let's see what that means. So first we need a ship. There's a ship. Now, it leaves port at noon. There's the port. Oh, and by the way, let's review how we do our directions. If we have north, east, southwest compass rose, and we see south, what's the number? South 29 west, that means, since we always start from north or south, the north-south line, and take the acute angle, it's a 29-degree angle west of south. So let's draw that in as a right triangle. Okay. Now, they tell us we're traveling at 20 knots, and a knot, K-N-O-T, is short for nautical miles per hour. So nautical miles per hour, we're going to go in that direction for 6 hours, which means hours cancel out, and we end up being 125 miles away on that bearing. Now the question asks, how far west did we go? So I'm going to label my west miles as M and my south miles as S, right? Because I can break that angular path into its 2 components, similar to X and Y when you were finding slope or anything like that on graphing linear equations. And so I know that that angle is 29 degrees. And like I told you, now I've got my right triangle, and now we know how to solve it. So check out, I'm going to have my opposite and my hypotenuse. So sine is going to be my function of choice. And sine of 29 degrees is m over 120. That distance west is going to be 120 times the sine of 29, which is 58.18. And there you have it. Let's move on to the next one. All right, next we have number 55. Two more to go, folks. Harmonic motion. So what we're going to do here is we are going to have a displacement at 0, or what the displacement is at t equals 0 of 0. The amplitude is 8 centimeters, and the period is 2 seconds. So let's visualize what this means. I'm going to draw myself a graph, and I know that the period of 2 seconds means it's going to do one full cycle of up, down, up in 2 seconds. So 1 second will be halfway, and we'll get these half seconds in there too. Now, one cycle going all the way around is 2 pi, right? So I'm going to split that similarly into 3 pi over 2 and pi over 2. All right, my amplitude of 8 means my sine wave is going to go up to 8 and down to -8. And then d of 0, meaning the displacement at time 0 is 0, meaning we're going to use the sine function because the sine starts at 0. Plot my sine at pi over 2, or 1/2 second. It'll be at the max. Then at 1 second back to 0, 1.5 at -8 and 2. And you'll see my butchered drawing there. Dare you to do better with a pencil and a tablet. And so I know that my equation is d displacement equals the amplitude times the sine of omega t. And looking from the box at the lower left, if my period is 2 seconds, my frequency is 1 over the period, or it'll be 1 cycle every 2 seconds, which will be 1/2 cycles per second. In this case, I go back over here and I see that the period is 2 pi over omega. Sorry, you can't see that very well, can you? Period is 2 pi over omega. And I'm going to use that. 2 pi over omega. So 2 is my period, is 2 pi over omega. And omega is going to be 2 pi over 2. Or pi. Now I can write my equation. D equals 8 times the sine of pi t. Which means, let's picture this through. At 1 second, when t is 1, I'm going to do the sine of pi times 1, which is sine of pi, and that's 0. That matches. If I do half, when t is a half second, right here, then this is going to be pi times 1/2, or pi over 2. Sine of pi over 2 is 1. 1 times 8 is 8. And that's how we turn harmonic motion into a sine or a cosine function. And the last problem we will do today is number 59, where we take the equation of harmonic motion and we answer a few questions about it. The equation we have is 4 times the cosine of 8 pi t, where t is in seconds. Okay, let's draw and let's figure out what this is going to do. So when t is 1 second, we will have gone 8 pi radians. First we're going to do the amplitude is 4 and -4, and there's my 8 pi. So in 8 pi radians, how many cycles am I going to do? I'm going to do 4 cycles. So if I split that up into sets of 2 pi, almost evenly, we have 2 pi for each cycle, so we'll go through 4 cycles in 1 second. I'm going to draw the points for 1 cycle. We'll see how this goes. Close. And then I'll throw another one in there so that we can see what the cycles look like. So the amplitude that I can get from the equation, part A, max displacement, or the amplitude, is 4. B, what is the frequency? So if the period, or the frequency, is how many cycles per second we have. And the frequency is 4 cycles in 1 second. Because where t is 1, we've gone around 4 times. For C, we want to find the displacement where t equals 5. So that's going to be 4 cosine of 40 pi. Now what is 40 pi? We know that one time around is 2 pi, 2 times around 4 pi, There's 8 pi. So by the time we go around 40 pi, we're going to be back to essentially 0. And the cosine of 0 is 1. So we're going to do 4 times 1 equals 4. Right? Now the way I'm going to show this is it's 20 times 2 pi and plus 0. So if you ever end up with like 21 or 41 pi, we're going to take that 40 pi out and it'll be the same as the cosine of pi in that case. And that's why I do take your 2 pi's out and see what's left. And that's all that you're going to do after 40 pi around. And then d is what is the lowest value of positive value of t where the displacement is 0. Right? So what we're doing is we're looking for this spot up here, right? First time it crosses 0. And we know from figuring this out that that's going to be pi over 2, right? But as far as time goes, it's 1/4, right? One cycle is 1/4 of a second, and then it's the first quarter of that. So it's going to be 1/16 of a second, or if you think about the period being the inverse of the displacement, it's 1/4 of the period. And I'll go up here and show that the period is 1 over the frequency, or is 1 cycle per, or it's 1/4 of a second per cycle. So there we have our answer. And that brings us to the end of this homework session. Hope you enjoyed it. Hope you learned something. I'm going to be jumping over to the Zoom meeting for anybody who has questions. Look on the Instagram feed or the Facebook feed, or it'll be down in the comments where the Zoom link is. And I hope that you enjoyed this, and come visit at rockpiletutors.com.